Good morning, ladies and gentlemen. This is Markus Rudolf from WHU, Otto, Beisheim School of Management. And today I would like to give you a little primer on risk-neutral pricing based on the state preference theory. In order to introduce the state preference theory to you, imagine a very simplified stochastic world where we only have two states of the world. Namely, we have an upstate here and we have a downstate. And in addition to the two states of the world, we have two securities. One is called a stock. The other one is called a bond. Now, the bond is a riskless security. In other words, it has the same payoff in both states of the world because it is riskless. The price today of the bond is 1,000 euros. Different to the bond, the stock is a stochastic security. So therefore, we have two different outcomes of the stock. Namely, in the upstate, we have an outcome of 1260. In the downstate, we have an outcome of 840 euros. The price of the stock today is assumed to be 1,050. Now, the core ingredient of state preference theory is a very special security which is called a pure security. A pure security is a security which pays 1 euro in the upstate and 0 euros in the downstate. So this is then the upstate pure security. And then we have a second pure security for the second state, which is called the downstate pure security, which pays 0 euros in the upstate and 1 euro in the downstate. In other words, what we are now trying to do is basically we try to combine the stock and the bond in such a way that we obtain a pure security for the upstate and a pure security for the downstate. So in other words, we have two states of the world and we have a simple linear equation which has to be solved with two unknowns. Namely, the first unknown is the fraction of the stock in our pure state portfolio, in our poor state security portfolio. And then we have WB, which is the fraction of the bond in the portfolio of the stock and the bond, which is supposed to be combined to an upstate pure security. So in other words, if we have WS times 1260, which is the payoff on the upstate, plus WB plus 1,050, which is the payoff of the bond in the upstate, then the value is supposed to be 1. And at the same time, if we have WS times 840, which is the downstate payment of the stock, plus WB times 1,050, which is the downstate payment of the bond, it is supposed to yield a return of 0. In other words, we have two equations here. And those two equations can be easily solved for the two variables, namely WS and WB. And the solution is that we construct the upstate pure security by investing 0.2381% into the stock and by going short by 0.1905% into the bond. Now if you resubstitute WS and WB into the equation, then we obtain an upstate pure security which pays 1 euro in the upstate and nothing in the downstate. Now at the same time, we are also constructing a downstate pure security, and the downstate pure security pays nothing in the upstate and 1 in the downstate. And then again we solve the two equations for WS and WB, and we obtain that the WS for the downstate pure security is minus 0.2381%. And the WB for the downstate pure security is 0.2857%. So in other words, we have four equations to be solved for four different variables, namely WS and WB in the upstate and WS and WB in the downstate. And then we obtain a portfolio of the stock and the bond which constructs the two pure securities that I was talking about earlier. Now, in other words, if you combine the stock and the bond, given that the stock costs 1,050 today and the bond costs 1,000 today, the price of the state 1 pure security is 0.2381% times 1,050 plus minus 0.1905% times 1,000, which is 59.52 cents. And at the same time, the state 2 pure security costs minus 0.2381% times 1,050 plus 0.2857% times 1,000. So the price of the state 2 pure security is 35 cents, a little bit more than 35 cents. Now please observe that if you combine the two pure securities, then you get a certain euro in the upstate and a certain euro in the downstate. So in other words, the combination of all pure securities is a riskless asset. Now, the price of the riskless asset should accord to the risk-free rate of interest. In other words, the price of the riskless asset here is simply the sum out of the upstate pure security price and the downstate pure security price. The sum turns out to be 95.24 euro cents, so 95.24 euro cents. Now, given that the bond price is 1,000 and that the payoff of the bond is 1,050, it is also quite clear that the risk-free rate turns out to be 5%. Now, the sum of the two pure security prices is exactly the same, like 1 divided by 1.05. In other words, it is the discounted value of 1 euro which I get with security after one period. So 0.9524 is nothing else than 1 divided by 1 plus r, which makes absolutely sense because the combination of both pure securities is a riskless asset. So therefore the return on the portfolio consisting of both pure securities should be equal to the riskless rate of interest. Now, this gives us basically a calculus for the evaluation of any arbitrary asset. Now, if you summarize what we have figured out earlier, we can simply say we have a WS for the upstate pure security, and we have a WB for the upstate pure security, and we also have a W down and also have a WS for the downstate pure security and a W down and WB for the downstate pure security. Now those are the values which we have calculated based on our example, and those are the two securities. So this is the upstate pure security, this is the downstate pure security. In other words, we have an equation consisting of we have a system of equations consisting of 4 equations, and this is the system of equations which has to be solved, namely the payoff matrix, which we call omega, times the matrix of the weights of those stocks and bonds which replicate the pure securities. That is supposed to be the unity matrix. So here we have the identity matrix, and the identity matrix simply indicates that we are talking about two pure securities, one which pays 1, 0 and one which pays 0, 1. Now the solution of that equation, of that system of equations, is comparatively simple because we simply have to invert the omega matrix and obtain the weighting matrix W. So the weighting matrix W, which gives us pure security weightings, is nothing else than the inverted omega matrix. Now that can be quite easily done. As long as you have two securities which are independent of each other. So our stock and our bond are independent of each other. So therefore the matrix omega of the payoffs has full rank. Given that it has a full rank, it can be quite easily inverted. Now, if we now take that observation and apply it to different assets, for instance, we apply it to a call option where the exercise price is 1,050. And please remember that the stock price was either 1260 or 840, depending on which state is going to occur. Now, if the stock price is 1260, then obviously the payoff of the call option is 210. And if the stock price is 840, then obviously the payoff of the call option is 0. Now the question is, what is the value of the call option today, given that it is either worth 210 or 0 in the next period? And the answer is comparatively easy, because we know already what the price of a pure security is. Namely, an upstate pure security costs 59 cents. In other words, every euro that I get in the upstate is worth 59 cents. In the case of our call option, however, I get 210 euros. Quite obviously, it is so that each of those 210 euros which I can get in the upstate of the call option is worth 59 cents. In other words, the upstate is worth 59 cents times 210. And accordingly, Each euro that I obtain in the down state is worth 35 cents. In the down state, in the case of the call option, we don't get anything. So in other words, the value in the down state of that call option is 0 times 35 cents, which is 0. So therefore, what we obtain and what remains is the value of the call option is 210 times 59 cents, which accords to 125 euros. So in other words, we have the prices of the pure securities. We can evaluate each state of the world based on the state preference theory. And that gives us the value of a call option, because a call option is a combination, obviously, of 210 pure securities in the upstate. And the value of 210 upstate pure securities is 59 cents times 210, which sums up to 125. The value of the call option is accordingly 125. Now we can apply the same thing to the put option. If we have a put option and the stock price goes up to 12.60, then the put option obviously expires worthless, at least if the exercise price is again 1,050. If, however, the value of the stock goes down to 840, and if the exercise price of the put option is 1,050, then it is so that in the down state, the put option has a value of 210, namely 1,050 minus 840. Now we can apply the same principle, because we know the prices of the two states. The upper state costs 59 cents, the lower state costs 35 cents. Now in the case of the put option, we get nothing in the upper state and we get 210 in the lower state. Now since the lower state is worth 35 cents for each euro, it is quite obvious that 210 euros in the lower state are worth 210 times 35 cents, which turns out to be 75. So the value of the put option is 75, the value of the call option is 210. Both based on the value of the pure securities, which are the central ingredients of state preference theory. And now finally, we can also try to evaluate a futures on our stock. Now what we know is that the futures price is the price of the stock times 1 plus the risk-free rate of interest. Because the cost of carry in the case of a futures contract is nothing else than the interest that you earn on the stock. Now, therefore, the futures price is 1102.50. Now, depending on where the stock price is going to end after one period, it is so that the value of the futures contract will be 157.5 if the upstate occurs. Namely, this is 1260 minus 1102.50. Or if the downstate occurs in the next period, then the value of the futures contract is 840 minus 1102.50, which turns out to be minus 262.5. So the payoff of the futures contract is now obviously either 157 or minus 262. The value of the futures contract today can be assessed by multiplying those cash flows which take place in the future by the state preference prices. Now the state preference price for the upstate as earlier is 59 cents. The state preference price for the downstate is 35 cents. In other words, if you multiply 157 times 59 cents minus 262 times 35 cents, it turns out that the value of the futures contract today is exactly 0. Which it should be, because initially the value of a futures contract is 0 if the futures price is selected correctly. Our futures price has been selected as 1050 times 1.05, in other words, times the spot price of the stock plus the cost of carry, which is 5%, and 1050 times 1.05 is 1102.50, and that implies a futures value of 0, which is absolutely correct. So this also proves somehow that the pure security prices have been correctly identified, because the futures price is correctly calculated based on those pure security prices. Now, if we generalize the whole approach a little bit, and if we say that we basically have two securities, one which starts with the value of 1 and it goes up to U with probability P, and at the same time it can also go down to D with probability 1 minus P. So that is, so to say, our stock, expressed much more generally than in the numerical example that we have observed earlier. And here we observe a bond. The value of the bond, the price of the bond today is again €1, but it goes up to 1 plus R or down to 1 plus R because it is a riskless asset. The bond is riskless and therefore it does not depend on the state which is going to occur. The upstate probability is P, the downstate probability is 1 minus P, but the price of the bond in both states is 1 plus R. Now, if we apply the same principle that we have derived earlier based on the numerical example, what we can say is that the weighting matrix for the stock and the bond is nothing else but the inverted cash flow matrix, the inverted payoff matrix of the cash flows. So in the case of the stock, we have U and D in the two states. In the case of the bond, we have 1 plus R in the two states. So in other words, this is our payoff matrix omega. If we invert the omega matrix, then we obtain this. This is the inverted omega matrix. In other words, this is omega to the minus 1. If we now want to assess the values of the pure securities, namely P up and P down. P up is the price of the upstate pure security and P down is the price of the downstate pure security. Then we have to multiply the weighting matrix by the outcome, namely the upstate pure security pays €1 in the upstate and the downstate pure security pays €1 in the downstate. So in other words, if we multiply that payoff vector of the two pure securities with the omega to the minus 1 matrix, in other words, with the weighting matrix, then we obtain the prices of the two pure securities. Now, if we multiply that, what we then obtain is that the price of the upstate pure security is 1 plus R minus D divided by U minus D times 1 divided by 1 plus R. And the downstate pure security price is U minus 1 plus R divided by U minus D divided by 1 plus R. So those are the two pure security prices, and those expressions are comparatively famous. Because what we can say is that, of course, the U factor must be more than 1 and the D factor must be less than 1. Otherwise, it wouldn't make sense to basically incorporate a risky asset. So a risky asset can either lose money or gain money, which implies that the U is more than 1 and the D is less than 1. Even more specifically, I can even say that the U must be more than 1 plus R. So U must be more than 1 plus R, because if I would not get more money in the case of the risky asset than for the riskless asset, nobody would ever purchase the risky asset. Right? If the risky asset, even in the best case, would yield less than the riskless asset, why should you ever buy the risky asset? And at the same time, D must be less than 1, as we have already said. Otherwise, it wouldn't make any sense, because if even in the downstate you get more money than the amount that you pay for the asset, then everybody would buy that risky asset and would gain money risklessly. So therefore, the U is bigger than the D, and the U is also more than the 1 plus R. If that is true, then we can say that this expression here, namely 1 plus R minus D divided by U minus D, is more than 0 and less than 1. Now let's call this expression pi. This expression pi is more than 0 and less than 1. And accordingly, U minus 1 plus R divided by U minus D, let's call that 1 minus pi, is also more than 0 and less than 1. We can even say that this expression plus this expression is equal to 1. So therefore we call it pi and 1 minus pi. Now the pi's are very essential now in the state preference theory. So what we have now derived is that the price of the upstate pure security and the price of the downstate pure security is pi divided by 1 plus R, respectively 1 minus pi divided by 1 plus r. So those are the pure security prices. What we can say about the pi's is that they are always between 0 and 1. By the way, just like a probability. So pi is not a probability, but it behaves a little bit like a probability, at least because it takes values between 0 and 1. Probabilities also take values between 0 and 1. So therefore, the pi's are not called probabilities, but quasi-probabilities, or martingale probabilities. So the pi is called a martingale probability, and it can be treated like a probability when you evaluate an asset. So what we do know is that if we do know the prices of the pure securities, then we simply have to multiply the pure security prices by the state-dependent payoffs of any security, and we obtain the price of that security. So in other words, if you want to evaluate a call option, and we don't know what the price of the call option is today, but we do know what the state-dependent cash flows of the call options are, then we simply multiply the state-dependent cash flows of the call option with the pure security price, and then we obtain the price of the call option today. Now, if we generalize that, what we can do is that the price of any derivative D is nothing else than the price of the pure security in the upstate times the value of the derivative in the upstate plus the price of the pure security in the downstate times the price of the derivative in the downstate. What we now can do is we can replace the P down and the P up by pi's and 1 minus pi's. So what I'm doing here is I have a pi times D up plus 1 minus pi times D down divided by 1 plus r, because we have the 1 plus r from here. And then we can say that pi times D up plus 1 minus pi times D down, this is something like an expected value, because we have a probability times an outcome plus a probability times an outcome. This is an expected value, with the only difference that pi is not really a probability. It is only a martingale probability. In other words, it's not an empirical probability, but it behaves like a probability because it takes values between 0 and 1. Now, if we interpret pi as a kind of probability, a martingale probability, we can then say that the expression in the numerator here is the expected value of D, where D is the payoff of the derivative. And that is discounted with 1 plus r. In other words, in order to obtain the price of the derivative today, we calculate the expected price of the derivative in the future and discount it with 1 plus r. Now, because we discount something which is risky with a riskless rate, this procedure is called risk-neutral pricing. So we price the derivative risk-neutrally. It is only important to recognize and to observe that risk-neutral pricing is not based on empirical probabilities. It is always based on martingale probabilities, and those martingale probabilities are not the real probabilities. Now, given that people are not risk-neutral in the real world, but risk-averse, it is so that the risk adjustment in that risk-neutral evaluation procedure is obviously not in the discount rate, but based on the martingale probability pi. Now, the martingale probability pi is not an empirical probability, but it behaves a little bit like a probability. It is similar to a probability. Now, this pricing procedure here is based on a discount factor, which is the risk-free rate of interest. Now, typically, if you discount a risky cash flow stream by a riskless rate, this is called risk-neutral pricing. So people who are risk-neutral don't care for the risk, they discount with a risk-free rate. So therefore, what we have here is called a risk-neutral pricing procedure. However, very importantly, risk-neutral pricing does not mean that people are really risk-neutral. Risk-neutral pricing only means that people discount with a risk-free rate, but they are using a probability instead of the empirical probability, which somehow has the risk incorporated. So our martingale probability pi obviously has to do with risk adjustments. So therefore, risk-neutral pricing, based on which the state preference theory has been developed, risk-neutral pricing is based on not a risk-adjusted discount rate, but a risk-adjusted probability, based on which the expected value is calculated here. So risk neutral pricing does not mean that people are really risk neutral. It only means that people are using different probabilities in order to be able to discount their expected cash flows with a risk-free rate of interest.